Hello, this is Dr. Mike Lee from Terra Systems. Today I'll be talking to you about combinations of emulsified vegetable oil or EVO with sulfidated ZVI. I'd like to acknowledge my co-authors, Richard Raymond, President of Terra Systems, and Paul Dombrowski of Isotec Remediation Technologies. Paul will be speaking to you a little bit later about some actual case histories for the application of this material. My presentation today will include an introduction, some batch studies, column studies, case history, and the conclusions. Anaerobic bioremediation is a natural process to clean up chlorinated solvents in the environment, particularly in groundwater. You're adding a carbon substrate, which is used as an electron donor to enhance biodegradation of the process. Has been used for more than 2 decades. Advantages include that it uses food-grade materials, it's a demonstrated effectiveness, low cost, and has longer persistence than other remediation technologies. Biological degradation of chlorinated ethanes proceeds from tetrachloroethane, PCE, to trichloroethylene, TCE, to cis-dichloroethylene, cis-DCE, to vinyl chloride, and finally to ethene or ethane. Many bacteria can carry out the first steps of this reaction from PCE to cis-DCE. However, only Dehalococcoides and Dehalobacter are known to be able to carry out the degradation of the cis-DCE to vinyl chloride ethene. The process may stall if Dehalococcoides or Dehalobacter are not present in sufficient numbers. Zero valent iron, or ZVI. The first application was for the treatment of pesticides in 1972. In 1990, there were a number of publications on the use of zero valent iron for chlorinated organic degradation. It's an abiotic reaction process. The first publications were back in 2000 on showing the iron degradation or ZVI process, some TCE to chloroacetylene and acetylene, so it's avoiding some of the side reactions producing cis-DCE and vinyl chloride. The chloroethylene and acetylene are typically short-lived products and then can be transformed further to ethene and ethane. The few of the important papers include the permanent reactive barrier technology update from ITRC in 2011, and papers in environmental science and technology and in groundwater. The first applications of ZVI occurred in the 1990s with ex situ soil treatment, soil tilling, and permanent reactive barriers or PRBs, typically through trenchant placement as shown in the figure on the bottom. A variety of different types of iron can be used, from coarse materials to finer materials. These are some iron products that are available from Hepburn Technologies. When you combine EVO and ZVI, you get both the benefits of both the biological and abiotic degradation processes. The abiotic process, again, may avoid some of the chlorinated intermediates such as cis-DCE and vinyl chloride. Other abiotic reactions can occur with minerals formed in the subsurface under anaerobic conditions. These include metal sulfides such as ferrous sulfide, siderite, sulfate green rust, magnetite. And these materials can react with chlorinated solvents to transform them. And this process can be engineered. There was a patent issued 6884352B1 for biogeochemical reductive dechlorination of bird by adding substrate, sulfate, and iron. Other workshops and papers have explored how to stimulate this process. Terra Systems conducted a number of batch tests looking at a variety of contaminants, chlorinated ethanes such as the PCE, TCE, or cis-DCE and vinyl chloride, chlorinated methanes, including carbon tetrachloride, CT, chloroform, CF, dichloromethane, DCM, and chloromethane. So these are produced biologically, and also you may get some of the intermediates produced with the ZVI. Chlorinated ethanes include 1,1,1-trichloroethane, or 1,1,1-TCA or 1,1,2-TCA, 1,1-dichloroethane, 1,1-DCA, 1,1-DCE, 1,1-DCE, and chloroethane. In addition, we've looked at brominated ethanes, bromoform, BF, dibromomethane, and bromomethane, and brominated ethanes, ethylene dibromide, EDB, and bromoethane as its degradation products. The batch studies used ZV loadings of between 0 and 15 grams per liter, ZVI particles of 4 to 125 or less than 125 microns, ZVI loadings of 3 to 10 grams per liter, used a variety of different sulfidation agents from sodium dithionite, sodium sulfide, sulfur, calcium polysulfide, and a ferrous sulfide solution. Bioaugmentation with the Dehalococcoides culture and also Dehalobacter were used in some of the batch studies. The first batch study used 1.2 to 5.6 milligrams per liter of chlorinated ethanes, chlorinated methanes, and brominated methanes. The study was run for over 70 days and evaluated the following treatments in the aqueous phase: EVO and bioaugmentation, 10 grams per liter of less than 125 micron ZVI, 10 grams per liter of the 125 micron ZVI with 0.7 grams per liter of sodium sulfide, 44 grams per liter of the less than 44 micron ZVI with 0.7 grams per liter of ZVI, 44 micron, 10 grams per liter at 4 ZVI, and then combinations of emulsified vegetable oil, 15 grams per liter, the 125 micron ZVI, and then with the sodium sulfide. This slide shows the percent removal of each class of contaminants for the different treatments. For the chlorinated ethane, there was little evidence for biodegradation, purple shown on the left. With the left 125 micron ZVI, the addition of sodium sulfide increased the sum of the chlorinated ethane removal from 55 to 87%. With the less than 44 micron ZVI, sodium sulfide increased the sum CE removal from 73 to 92%. So there's somewhat higher reactivity with the smaller ZVI particle. With the 15 grams per liter of the EVO and the less than 128 micron ZVI, sodium sulfide increased the sum chlorinated ethanes removal from 73 to 80%. The chlorinated ethanes, chlorinated methanes, and brominated ethanes were treated more completely than the chlorinated ethanes. The addition of sodium sulfide increased the extent of degradation over the ZVI particles alone. Batch 2 also evaluated chlorinated ethanes, chlorinated methanes, brominated methanes, and brominated ethanes at concentrations between 0.8 and 4.2 milligrams per liter. This study was carried over 28 days. Treatments included unlimited control, 10 grams per liter of the 4 micron ZVI, 10 grams per liter of 125 micron ZVI, 10 grams per liter of a 44 micron ZVI, and 10 grams per liter of the 44 micron ZVI with the 3 grams per liter of sodium dithionite, 15 grams of EVO, 10 grams per liter of ZVI, and then that combination with 3 grams per liter of sodium dithionite. In conclusion, the 4 micron ZVI gave the highest removal of the chlorinated ethane, 75%. A slight improvement of the 44 micron ZVI of 58% was present over the 125 micron ZVI. The sodium dithionite didn't improve the activity of the 44 micron ZVI, 43%. Sodium dithionite did increase reactivity of the 44 micron ZVI, and EVO did 64% of the treatment with the 44 micron ZVI without the dithionite, and that included the EVO at 33%. Chlorinated ethanes showed similar reactivity to the chlorinated ethanes. All the ZVI treatments showed higher reactivity against the chlorinated methanes, brominated methanes, and brominated ethanes than the chlorinated ethanes and ethanes. Batch 3 used 67% soil, chlorinated ethanes, brominated ethanes, chlorinated ethanes, and chlorinated methanes, concentrations between 3 and 4 milligrams per liter. This study was carried out over 43 days. Treatments included 6 grams per liter of the 4 micron ZVI, 3 grams per liter of the 4 micron ZVI with 0.2 grams per liter of sulfur, 7 grams of the ZVI with 10 grams per liter of EPO, 4 grams per liter of the 4 micron ZVI with 13 grams per liter of EVO and 0.2 grams per liter of, and then combination of the 4 grams per liter of 4 micron ZVI with 13 grams per liter of EVO and 0.2 grams per liter of sulfur and Dehalococcoides. The 4 micron ZVI with sulfur gave the highest removal, 99% of the chlorinated ethanes compared to 89% with the 4 micron ZVI alone. EVO and ZVO resulted in 80% removal. The additions of sulfur to the EVO and the 4 micron ZVI increased the sum chlorinated ethanes removal to 88%, and with the DHC, the sum chlorinated ethane removal was 94%. Again, chlorinated ethanes and chlorinated methanes showed similar results to the chlorinated ethanes, with the addition of sulfur and bioaugmentation culture increasing the extent of removal. Batch test 4 used 50% soil. Again, evaluated chlorinated ethanes and 1,2-dichloroethane concentration between 0.3 and 60 milligrams per liter over 127 days. Again, the treatments included a control, 8 grams per liter of a 4 micron ZVI, and 4 microns per liter ZVI with 8.8 grams of a ferrous sulfide solution, combination of EVO, the micro ZVI, and the ferrous sulfide, and then finally the Dehalococcoides was added. Conclusions: the 4 micron ZVI with that ferrous sulfide gave the highest removal to 92% of the chlorinated ethanes compared to 88% with the chlorinated with the 4 micron ZVI alone. EVO, ZVI, and ferrous sulfide resulted in 74% removal. The additions of the ferrous sulfide and DHC to the EVO and 4 micron ZVI showed us some chlorinated ethanol removal of 66%. The chlorinated ethanes showed higher removal than the chlorinated ethanes, with their maximum removal of 97% with the EVO, 4 micron ZVI, and the ferrous sulfide solution. 1,2-dichloroethane removals were much lower, ranging from 37 to 54%, with the highest with the ZVI only. Batch test 5 used 67% soil, 0.3 milligrams per liter of TCE and 0.3 milligrams per liter of BC over 48 to 84 days. Treatments were control, 2 grams per liter of EVO, 2 grams of EPO with the Dehalococcoides, 5 grams per liter of ferrous sulfide alone over 48 days, 10 grams per liter of EVO, and 5 grams per liter of the ferrous sulfide over 48 days, and finally a treatment that combined the 10 grams per liter of EVO, 5 grams per liter of ferrous sulfide, and Dehalococcoides over 48 days. Conclusion: the sum chlorinated ethanes were 31% in the control, 43% with the 2 grams per liter of EVO, 99% with the 2 grams per liter of EVO plus Dehalococcoides, 5 grams per liter of the ferrous sulfide gave 75% removal. When you added the EVO and 5 ferrous sulfides, were up to 86%. And then finally, the combination of EVO, bioaugmentation culture, and ferrous sulfide gave a removal of 80%. Almost complete dechlorination was observed with EVO and DHC over 84 days. The ferrous sulfide showed 75 redemption in some chlorines over 48 days compared to the control loss of 31%. The addition of the EVO and ferrous sulfide performed slightly better than the ferrous sulfide alone. So, in conclusions, generally see higher extent of degradation with ZVI or EVO plus ZVI than EVO and bioaugmentation, although we do have cases where it's gone completely to ethene with that combination of EVO and bioaugmentation. This may take a little longer. Improvement of degradation extend rate with EZVI and sulfidation agents. A variety of sulfidation agents worked for PC and TC. 1,1-TCA, 2-TCA, chlorotet, chloroform, bromoform, and ethylene dibromin almost went to completion with just ZVI. 1,2-dichloroethane was not treated as effectively, although it is aerobically and anaerobically biodegradable. Sulfidation agents from sodium sulfide, sulfur, sodium dithionite, ferrous sulfide solution, and calcium polysulfide all worked to improve the degradation rates with the ZVI. A low sulfur to iron ratio is required, so the improvement with sulfidation for the small micron compared to the moderate 125 micron ZVI particles. Incorporation of substrate with ZVI reduced the chlorinated ethane treatment in some cases, but expect more degradation to occur in situ with longer treatment times than in the batch studies. Complete degradation with EVO and bioaugmentation is possible, but often slower than ZVI plus sulfide plus EVO. And the ferrous sulfide solution alone or in combination with EVO and bioaugmentation culture showed some improvement over the control or EVO alone, but wasn't complete after over 48 days. Next, I'm going to describe some column tests we conducted. These were sand columns prepared. They were about 5.1 centimeters in diameter and 35 centimeters long. Average retention time was 2 to 2.9 days. Contaminants included 1 to 3 milligrams per liter of TC, 3 to 5 milligrams per liter of chloroform, and 0.7 to 3 milligrams per liter of 1,1-trichloroethane. EV loadings were 0 or 15 grams per liter, 4 micron ZVI, 10 grams per liter per kilogram, sulfidation agent at either 1 and 5 grams per kilogram, and then bioaugmentation with the TSI Dehalococcoides culture and the Dehalobacter culture was conducted on day 15, and then ferrous sulfide was added to the influent on day 17. And these studies were carried out for over 28 days. So this just shows a picture of the columns. You see the columns, 12-inch columns, and collecting our influent samples, and the effluent samples were collected in Tedlar bags to control the amount of oxygen infiltration and to collect the volatils and dissolved gases for analyses. So this is showing the complete some of the chlorinated ethane removal for each of the columns. This is on a micromolar basis with daughter products. The ZVI alone had an average chlorinated ethane removal of 67% and SRS Z of about 74%. We see an improvement with the addition of the ferrous sulfide to the ZVI. Average removal of the chlorinated ethanes is 92%. SRS with a low ferrous sulfide solution averaged 94%, and the SRS Z with a high ferrous sulfide solution averaged 92%. So it doesn't appear to be any particular advantage to adding more of the ferrous sulfide solution. The sum chlorinated ethane was highest on day 28 after bioaugmentation, and the ferrous sulfide was added to the influent. The ZVI had average some chlorinated methane removal of 45%, and the SRS Z a little bit lower at 40%. The addition of the ferrous sulfide to the ZVI increased the average chlorinated methane removal to 56%. With the SRS Z, with the emulsified oil and zero phenyl iron, and low ferrous sulfide were up to 91%, and a slightly better improvement with a high ferrous sulfide solution of 5 grams per liter. The ZVI column had an average chlorinated ethane removal of 53%, and the SRS Z with EVO and ZVI about 58%. The addition of the ferrous sulfide to the ZVI increased average chlorinated ethane removal to 89%, and then the treatment with the low ferrous sulfide in ZVI and the EVO averaged 82%, and the high SRS with high ferrous sulfide averaged 86%. Next slide shows reaction times and percent removal of the chlorinated ethanes, and chlorinated methanes. The TCA half-lives range between 0.3 to 1.5 days, with between 2.8 and 14.1 days to reach the MCL of 0.005 milligrams per liter. The highest TCA removals were with the SRS Z, low ferrous sulfide, but we see more daughter products accumulated. The 1 TCA degradation half-lives were 0.2 to 1.5 days. The highest chlorinated methane chloroform degradation was with the SRS Z and low ferrous sulfide. Again, the FES increased the chlorinated ethane removal over the ZVI or SRS Z columns. In conclusions, the ZVI and EVO treatments amended with the ferrous sulfide outperformed the columns without the FSS. EVO plus ZVI with the low ferrous provided the most complete degradation of the TCE, 1-TCA, and chloroform. Addition of the bioaugmentation cultures on day 15 and/or the ferrous sulfide solution on day 17 of the influent increased the extent of dechlorination at day 29 compared to day 22 for all treatments. More chlorinated ethane degradation products, ethane and acetylene, were generated with the ferrous sulfide than without the ferrous sulfide. Less dichloromethane and chloromethane from chloroform, and 1,1-dichloroethane and 1,1-dichloroethane and chloroethane from TCA were generated with the ferrous sulfide. Enhanced VOC chlorination extended degradation rates with the sulfidated ZVI. The laboratory studies were not cut long enough to be able to show the increased longevity of the sulfidated ZVI that's been reported by others. Next, talk a little bit about a pilot study that was done, a fairly small pilot, about 900 square feet, 9 direct points on 11-foot spacing. The reagents included the SRS small droplet, EVO, the SRS Z with a 2-micron ZVI, sodium bicarbonate, and then a bioaugmentation culture. About 2,300 gallons of total solution was injected, which included 500 grams of deoxygenated, or gallons of deoxygenated water. And the groundwater contains about 200 to 270 milligrams per liter of sulfate. So these are results from 2 to 4 months after the injection. We have 2 different areas. In the injection area, we're seeing more of a biotic signature with complete reduction of the PC and TCE with very little daughter products. And then in the down gradient area, we're seeing more of an abiotic or biological signature with the reduction of TCE to cis-DCE. We already see evidence for baseline sulfate reduction or ferrous sulfide generation with the baseline high sulfate concentrations. In conclusion, sulfidation increased reactivity and the extent of chlorinated and brominated compound degradation by ZVI. A variety of sulfur compounds at low concentrations are effective with ZVI, including sulfate in groundwater or added to groundwater. And then the combination of emulsified vegetable oil, ZVI, sulfidation, and bioaugmentation were effective for promoting degradation, although longer reaction times may be required than with ZVI or the sulfidation agents. I'd like to thank you for your attention and take any questions. Thank you.